Imagine being on Mars for the very first time. The rust-colored dust crackles under your feet. The sky is a butterscotch-colored haze. Because this world is smaller than the one you left behind, the horizon curves a little more sharply than you're used to. From everything you've ever known, you're on a world 225 million kilometers away. Think about the moment it hits you. You'll never return home. No, it's not because the rocket broke or the mission was canceled. It's because your body, the one that got you here, has already started to lie to you. Plus, by the time you try to make the trip back, it will no longer be able to live on Earth. This is not a guess, this is science. We're going to talk about why the first people who go to Mars will probably have to stay there forever in this movie. First, let's be clear about one thing. Engineers aren't the biggest problem when it comes to getting back from Mars. It's not money, fuel, or launch slots. It is the body of a person. We are perfectly tuned for living on Earth. Every heartbeat, every bone, and every muscle fiber is set to a different world with a different gravitational pull. If we are taken out of that setting for a long time, the calibration will no longer work. An ISS rotation every 6 months is not a journey to Mars. 2 to 3 years is the earliest possible time frame. 6 to 9 months to fly there, and about 18 months to wait on the ground while the planets readjust, then fly back for another 6 to 9 months. During every day of that trip, the astronaut's body breaks down in ways that can't be fixed after a certain point. In general, Mars is about 225 million kilometers away from Earth. That number drops to about 55 million kilometers during a good opposition, when both planets are lined up on the same side of the Sun. It would take over 60 years to drive at highway speed without stopping, almost a whole human lifetime just to get there. As you might expect, spacecraft move faster, but it still takes 6 to 9 months each way with our best chemical engines. That's more than a year of flight time in a metal box under pressure. And during those months, there is no weight at all. Your body floats, and your body sees the lack of weight not as freedom, but as a sign to turn off the systems it doesn't think you need. Every second on Earth, your body works against gravity, which you can't see. Your bones and muscles have to stay strong because you stand, walk, and even sit up straight. The method is based on demand. If you take away that desire, the body will do something very efficiently. It starts reusing things it doesn't need any longer. In space, bones lose about 1% to 2% of their mass every month. A person in space can lose up to 12% of their bone mass after 6 months. After a year, it could be 24%. This harm is mostly found in the bones you need the most on a planet. The hips, the spine, the femurs, and the other bones that support your body weight. In general, a woman over 70 who has serious osteoporosis has lost between 30 and 40% of her bone mass. It took decades for that to get worse. In less than 2 years, a healthy person in their 30s can get close to those numbers. The process works in a sneaky way. When the body finds bones that aren't under any stress, it slows down formation and speeds up breakdown. Your kidneys get rid of the calcium from your breaking down bones, which greatly raises your risk of getting kidney stones. Although medical care is very limited in some places, muscles still move in the same way. When you don't have gravity, your back, leg, and core muscles quickly lose strength. The types of fibers change, going from slow endurance fibers to fast twitch fibers that get tired quickly. The astronauts on the ISS work out with special resistance tools for 2 hours every day. They still lose weight. They can stop the fall. They can't stop it. Now here's the catch. In cosmic words, the ISS is only 400 kilometers above Earth, which is very close. They stay there for 6 months, and many of them can hardly walk when they get back. They need to be taken out of the box. It can take weeks or even months to fully recover, and some people will never have the same bone mass again. That's after 6 months of constant help from the ground and knowing that help is always on the way. After that, increase that time frame by 4 or 5. Take the support off the ground. Take away any chance of coming back early. That's a trip to Mars. The body has no idea that you're coming back. Month after month, it just keeps taking itself apart with mechanical apathy. But not having any weight isn't the only danger. There's something worse that you can't see, feel, or get away from at all. Radiation from space. Earth has a magnetic field and an atmosphere that protect us. Every year, you take in about 3 millisieverts of radiation. That number goes up to about 150 on the ISS which is still in Earth's magnetosphere. That safety goes away completely in deep space. As stars explode all over the sky, heavy ions, cosmic rays, and protons fly right through the walls of spacecraft like they're not there. This is not a peaceful photon. Particles moving at speeds that are very close to the speed of light. They get into the brain, muscles, bones, and skin. Every time they hit something, they break DNA strands. Radiation levels on a round trip to Mars are thought to be between 900 and over 1,200 millisieverts. NASA has 600 jobs available. That limit would be broken by a single trip to Mars before the crew even gets there. And the damage builds up over time and can't be fixed. DNA damage from radiation builds up over time, while sunburn heals quickly. Every particle hit adds up to the whole. There is too much damage for your cells to keep up with while they try to fix the breaks. Errors add up over time, months, and years. Changes are added on top of changes. If you wait long enough, the chance of getting cancer rises until it is statistically certain. However, cancer is not even the most important thing right now. New research shows that cosmic radiation can cause measurable cognitive decline, including memory loss, slower reaction times, and trouble making decisions, exactly the skills you'd need when one mistake could kill everyone on board. We also can't really protect ourselves from it. Secondary radiation, which is sometimes more dangerous than the original particles, is made by walls that are thicker. There isn't a clean way to solve the problem. The heart is the organ that keeps everything else living. About 100,000 times a day, your heart beats against gravity to bring blood to the brain. It stays strong because of that ongoing work. That resistance goes away in microgravity, so the heart changes, which is a fancy word for shrinks. Long trips can cause astronauts' hearts to lose up to 20% of their mass. The blood also moves around. Body fluid builds up in the head and chest when there is no gravity. The body sees this as too much and gets rid of the fluid. Up to 20% less blood is in the body. The heart gets used to having less work to do, and it shrinks to fit a smaller body. The trouble starts as soon as gravity goes back to normal. The heart suddenly has to push blood up at full force, even though it is much weaker than it used to be and has a lot less blood to work with. This leads to orthostatic sensitivity, extreme dizziness, falling blood pressure, and passing out. After 6 months, some workers on the ISS can't even stand up. After 2 to 3 years on Mars, they have to be caught by rescue teams as soon as they get out of the capsule. It would be a lot worse if the situation got worse. It wasn't just that the heart hurt, it's possible that awareness wouldn't last at all in Earth gravity. After years of changing to handle less demand, a pump was suddenly asked to work at full capacity in a world 3 times heavier than the one it knows. When you add in atherosclerosis caused by radiation and vessels that are hardened and calcified, you have a cardiovascular system that can't work on Earth. You might believe that's the worst thing that can happen. It's not. When you are in microgravity, the fluid pressure in your brain goes up. This pushes on the back of your eyeball and changes its shape. The retina warps, the optic nerve swells, and the lens flattens. Some astronauts who go on 6-month trips to the ISS need glasses or contacts when they get back. Some people go through changes that they can never fully undo. The pressure has more time to do its job the longer the task. On a trip that lasts more than 1 year, the worry isn't just blurred vision. It could cause lasting damage to the optic nerve. There is damage that can't be fixed with glasses. The brain comes next. Studies on animals that used simulated cosmic radiation show that it does a lot of damage to the nervous system, causes chronic inflammation in brain tissue, and leads to the loss of dendritic spines, which are tiny structures that neurons use to talk to each other. Less spines means less connectivity, which makes you think and remember things more slowly. The effects on behavior are very clear. More anxiety, trouble learning where things are, and a harder time telling the difference between known and new environments. These are exactly the kinds of thinking you'd need to get around in a strange world. No one has ever spent years outside of Earth's magnetosphere, so we don't have any long-term records from people in space. But the animal models show something that isn't right, and there's no reason to think that people would be safe. Let's look around. 6 months pass before an astronaut steps foot on Mars. During that time, they lose bone, muscle, and heart mass. It's possible that their eyes have changed shape. Radiation damage is building up in their DNA. They may not be thinking as clearly as they used to. You might think, well, at least there is gravity on Mars. 38% of Earth's surface. That must make things better, right? This is where it really gets scary. Mars has a third of Earth's gravity. It would feel like about 27 kilograms to someone who weighs 70 kilograms. Even though it sounds almost freeing, no one has ever lived in half gravity for a long time. We only have data from two extremes, Earth at 1G and the International Space Station at 0G. Between these 2 points is a huge question mark. Scientists think that 0.38 grams is probably not enough to keep bone density and muscle mass at levels that are normal for Earth. Compared to 0 grams, it might slow the drop, but slow does not mean stop. Take a look. When you're on Earth, gravity makes you weigh what you do. Your body is made to fit that shape. The need goes down by 62% on Mars. Your body knows that the load has gone down and keeps getting rid of what it sees as extra structure. There are fewer and fewer bones. The muscles are getting weaker. It takes longer for the heart to get used to less work than it did in 0G. 18 months of this. 18 months of slowly getting your body ready for a lighter world. Then there's the trip back. After everything that happened before, another 6 to 9 months in heavy space, the astronaut's body has been in low or no gravity for 3 years straight by the time the capsule gets to Earth. The damage over time is shocking. The pilot will feel 1G for the first time in almost 3 years when that capsule hits the ground. Full earthly gravity is the force that their body was made to handle, but has been forgetting for years. Bones that have lost 40 to 50% of their density could break just by standing up. Since the heart was weaker and smaller, it would be hard for it to push blood against gravity. The pilot could pass out within seconds of attempting to stand up. Their muscles would weaken under the weight of Earth because they had been changed to fit a third gravity world. Think about that. The astronauts have spent years traveling, billions of dollars, and been on the biggest mission ever. When they get back home, they can't stand up. It's not an exaggeration. It's projection from real data from the ISS over a 3 to 5 times longer period of time. And every piece of information we have points to the same result. Why can't we figure this out? The honest answer is that we're trying, but the answers are either not good enough or won't be ready for decades. Working out is good for you, but it doesn't solve the problem. Even though astronauts train hard every day, they come back from the ISS weaker. Being on a machine and not having gravity is like trying to beat biology. To keep people from getting very sick from the motion, a structure at least 50 meters in diameter would be needed for spacecraft spinning to create artificial gravity. It's much harder than anything we've tried to build and spin something that big in space. Researchers are looking into drugs that can slow bone loss, but long-term missions have not yet shown that they work. Shielding against radiation adds weight, which means more fuel is needed, and the rocket math is very strict. At the moment, we don't have a technology or set of technologies that can keep the human body ready for a 3-year journey to Mars. We've got ideas, we have programs for study. We don't know the answer, not yet. This is where the subject changes from biology to philosophy. If going back to Mars is physically impossible and might even be dangerous, then every rough mission to Mars has to be a one-way trip, not because the scientists want it to be, but because biology and physics say it has to be that way. There will be no going back for the first people who walk on Mars. They will have to accept this before they even leave. They are told that the red dust they step on will be them for the rest of their lives. Their bones will turn into bones from Mars. They'll have hearts like people on Mars. It won't be as heavy on them in that world than it is on Earth, and will no longer be able to live or work in the world they came from. Giving up something like that is weird, not big or happening right away. There was not a single brave moment. It's slow, quiet, and cell phone-like. The body moves away from Earth a little more each day on Mars, not miles, but in terms of what they can do. There comes a time when a certain point is reached, a dead end that has nothing to do with fuel or the way orbits work. It's written in their DNA, in the mass of their bones, and in the strength of their hearts. Something very humble about this abounds. We can make rockets that can go through space between planets. We can plan places for aliens to live. That being said, we can't undo 4 billion years of development in just a few decades. Our bodies are made by Earth's gravity, its atmosphere, and its magnetic field. If you take that away, the body changes. It changes into something that works in a different setting. And when it goes to Mars, it stops being fully Earth. The first people to live on Mars will be more than just scientists. They'll live there. In the beginning, people knew that touching another world meant giving up this one. That could be the price we pay for going further than our bodies were made to go. It's possible that every big step needs to leave something behind. I hope this video was fun for you. If it gave you something to think about, I'd really appreciate your support. Have a nice trip.